channel components are widely used in industries such as injection molding, pneumatics, and thermal management. Customer requirements often vary greatly. Some need transparency, others require sealing, and some demand localized conductivity. However, challenges emerge once these requirements are translated into the actual processing stage. Internal flow channels are invisible and hard to measure. Thin wall structures are prone to deformation, and special materials impose additional CNC constraints. How does WayKen respond? 3 cases to show how we think. Case number 1, Elton dual solenoid valve manifold. The customer's requirements were clear. The part needed both good mechanical performance and transparent flow channels to allow direct visual inspection of airflow during testing. The material chosen was Elton 1000, a high-performance engineering plastic. So beyond managing heat during processing, another challenge arose. Although the material itself is transparent, CNC machining leaves the surface frosted, reducing clarity and making the internal flow channels hard to see. WayKen's solution is that after CNC finishing, add a vapor polishing step. It restores optical clarity to the inner walls of the flow channels. Final results: transparency meets visual inspection requirements, and the mechanical performance meets specifications. Case number 2, automotive air conditioning system flow channel plate. This part has specially curved internal flow channels and high sealing requirements. Flatness after welding must be controlled within 0.3 mm. The challenge is that due to the curved structure, the part cannot be machined directly from a single block. Therefore, the part must be split into upper and lower halves, machined separately and then welded together. But conventional welding has 2 issues: large welding seams and a large heat effective dome. Air tightness is difficult to guarantee, and flatness is hard to control. We can use a friction welding. This is a solid-state joining technology with a small heat effective dome. No porosity or slack inclusions, weld strengths close to that of the base material, and controllable deformation. Both air tightness and flatness achieve the customer requirements. Case number 3, pneumatic equipment manifold. The customer required hard anodizing of the entire flow channel with a layer thickness of 25 to 30 microns. The purpose was to increase surface hardness, enhance wear resistance, and improve corrosion resistance for long-term use in pneumatic equipment. At the same time, the area around the flow channel must retain electrical conductivity. Additionally, the positional accuracy of critical holes is required to be between 0.1 and 0.3 mm. This creates a contradiction. Anodized layers are insulating, but specific areas need conductivity. Our approach was multi-step. During machining, a Delton anti-deformation process was used to control stress in thin wall area of the flow channel. After anodizing, for holes with strict positional accuracy requirements, a secondary machining step was performed to remove the anodized layer, restore conductivity, and correct tolerances. For areas without strict positional accuracy requirements, localized laser engraving was used to remove the anodized coating. Finally, all areas where the anodized layer was removed underwent chromate treatment to achieve both corrosion protection and electrical conductivity. Final results: anodized layer thickness met the requirements, resistance in conductive area around the flow channel ends was within specification, and the positional accuracy of critical holes remained within tolerance. Transparent visualization, curved sealing, localized conductivity. 3 cases, different requirements, matched with different combinations of processes. For flow channel component manufacturing, WayKen ensures that we select the right solution based on the customer's specific needs and execute every step properly. If you have similar manufacturing requirements, feel free to contact us. Let's discuss your process solution together.